Hello everyone, here is Unit 6 of AP Physics 1. Now this one deals with rotation and energy as well as momentum. So as always, this is going to be kind of a crash course. It's going to be focused on problems. So I'm going to give kind of a brief concept overview and then go into some problems. The problems are going to be where you do most understanding. So if you don't understand it immediately when I'm just going over the concept, it'll make more sense in the problems. If you're just using this as a very quick review, you can skip right to end where I'll do kind of an overview as fast as possible, everything you need to know for this unit. So without further ado, let's start with 6.1. So everything you need to know about 6.1 is just that we have rotational kinetic energy. So they can have both translational and rotational kinetic energy. So I want you to imagine your friend throwing you a football. That football will travel, kind of its center of mass will travel, something like that. And you already know how to calculate that kinetic energy just using 1/2 mv squared. You learned that in Unit 3. But it'll also spiral around and it'll be rotating. Now the way you account for that is rotational kinetic energy, which is 1/2 times the rotational inertia times its angular velocity squared. Now this is very parallel to the formula here. You'd learn these parallels in Unit 5, how rotational inertia is like mass, angular velocity is like velocity. And then also the total kinetic energy is equal to the sum of these two parts, rotational and translational. So that's just something to know. So they're both scalar also. And a rigid system could have non-zero rotational kinetic energy, even if the center of mass is at rest. So what that means is like you could have a ball that's spinning around, but its center of mass isn't moving. In that case, it would have non-zero rotational kinetic energy, even though the center of mass would be at rest. You can picture like a fidget spinner. Let's go over the first problem now. So we have rotational inertia here, as well as an angular velocity for this disk. So find its rotational kinetic energy. So as always, pause and try and solve this problem by yourself. And then what we see here is that we can use the formula 1/2 I times the angular velocity squared. And this disk will be spinning around, right, like that. And just think about its rotational inertia for a second. Go back to Unit 5. The rotational inertia of a disk, it includes kind of some of these points out here. So say this disk had a narrow radius. It would have a much smaller rotational inertia, right? So that's just some stuff to think about regarding the past unit. And then if we just go into the formula, we can just plug in 2.5 times 4.0 squared. That'll give you 20 joules. You can just calculate that out. That's just plugging directly into the formula. But the important part to consider, just that you need to understand, is you picture this disk spinning. It's not moving anywhere, right? Just picture like a disk, say, on a vinyl player or something like that. It's not moving anywhere, but it still has some energy, right? It still has some energy of motion. And in order to kind of calculate that, all we're doing is we're using this moment of inertia, rotational kinetic energy formula. Now, if you want to derive this formula by yourself, you could. So the way you do that is you think about how some of these kind of points along here, you'd have to relate the rotational velocity to its translational velocity using the radius. Now, you would have learned how to do some of that in the past unit. But that's kind of an exercise that you can do. You don't need to know how to do that, so we can just kind of focus on just plugging directly into there. And then the second part, if it doubles its angular speed, by what factor does the rotational kinetic energy change? So for this one, if you double the speed, you're doubling this part, and this is a squared quantity. So obviously if you double something that's squared, the total factor that it'll be changing by is 4, because it's 2 squared. So in other words, if you change this to 8, it would be at 80 joules. And you can do the math out for that, or you can just kind of look, okay, we're doubling this, and that's getting squared. So that's all for 6.1. Now let's move into 6.2. So this one, it works very similarly to the linear work. This is kind of rotational work. So all this is saying is that the work done by constant torque would be this torque times the angular displacement. Now remember, for translational work, it'd be the force times the distance and displacement. So this kind of works exactly the same way, where we just multiply this torque by this angular displacement. And then also in a graphical sense, it would be the area under a torque and angle curve like this. That's because whenever you have a graph, an area would be like the multiplication of the y-axis and the x-axis. That's just something that's like good to know. A slope would be dividing the two, and so on. Anyway, so let's go into problem 2. So this wheel, so we have some wheel, and it's subject to a constant torque of 3 Newton meters as it rotates through 2 radians. So let's just visualize that. So let's just say someone's spinning this wheel, putting their hand on it, and spinning it with 3 newtons of torque until about like here, right? That's about 2 radians because this is 3.14. So they're just rotating like that. You can think of like a steering wheel or something. So calculate the work done by torque. Right? So we know that work is equal to torque times angular displacement. So here we can just kind of plug it in, so it's just 3 times 2. That's 6 joules, right? So in other words, we're adding some energy into this wheel as we're just kind of steering it, right? It's gaining some angular velocity, we're putting some acceleration into it by applying this torque. Now we can just kind of think about the Newton's second law in rotational form. If we're applying some torque to this system. And anyways, so we're increasing its rotational kinetic energy, which means that some work is being done. So if the wheel's initial rotational kinetic energy was 5 joules, so maybe the wheel is already spinning, what's its final rotational kinetic energy? We know that work is equal to the change in net kinetic energy. Now here we're only moving rotationally, so it's only going to affect the rotational kinetic energy. Because there is no translational kinetic energy, this wheel is assumed to be moving at some kind of constant, either some constant speed translationally or just at rest. So here the total work would be a change in kinetic energy, so we can just add these up and say that the final rotational kinetic energy is 11 joules. Now, if you don't understand what I did there, make sure you review Unit 3, where you go over the relation between work and energy. So, as you can see, there's a lot of parallels between the angular energy and the translational energy. Now, for angular momentum, as per before, there's a lot of parallels. So if you have a rigid body, it works by the formula, it's just this. Point mass is just that. These are all in your formula sheet, so don't worry too much about memorizing them, but you should try and conceptualize them just a little bit. So in terms of angular velocity, it's really just linear velocity times your radius, right? Because this is mv, and then we have some radius here. So that's how you do it for a point. And then for a rigid body, it's just kind of the summation of all of those. So that includes its kind of rotational inertia bit as well. And you'll understand this part as we go over problem 2. So you're going to choose a point to go around angular momentum, and that kind of matters. And then also there's angular impulse, which is just the change in angular momentum. That's equal to net torque over time. Again, we'll go over that a bit more in detail. And then the net torque is the slope of this angular momentum and time graph, because we're just dividing these two quantities. So whenever you divide something in a graph, it'll be the slope, the y-axis over x-axis. So whenever you think about like graphing problems, just know that like if you're multiplying, that's an area. If you're dividing, that's a slope. So again, like if you have some torque here, the area under this would be the impulse because we're multiplying, right? So now let's go over problem 3. So this one shows a uniform disk spinning around its central axis with an angular velocity, and then we have a constant frictional torque. So find an angular momentum originally, right? So here we can just plug directly into the formula. So its original angular momentum is going to be 2 times 10. So that's 20 kilograms times meters squared over second. It's kind of some awkward units, but this is kind of the units for angular momentum. So that's our initial angular momentum just by the formula. Now, determine the time t it takes for the disk to come to rest. Now, here's where we can kind of apply the knowledge from this unit. So we know that the change in angular momentum is equal to the torque over time, and we have some torque, and we have it's applied for some time t, right? It's coming to rest, And we know that this change in angular momentum, the final angular momentum must be zero because it can't be rotating when it's at rest, right? So we know that delta L is equal to LF minus Li, and LF will be 0, so it's going to be 0 minus 20. So delta L is minus 20. And we know that delta L is equal to torque times the delta time. So if we set this up, we know that the torque is 5 Newton meters, right? So that's just going to be 5. However, one thing to note is that it's moving opposing the motion, right? So then the torque is going to be minus 5. If it was in the same direction as the motion, we'd put it as positive 5, but it's opposing it. So that's minus, that's delta t. And then now just solving, we see that delta t will be equal to 4. So in other words, the disk has some angular momentum originally, and then it slows down, right? So it's moving like this, and then it's slowing down. And when it's completely at rest, there's no angular momentum, and that's by some frictional force. And this is the formula that shows that change in angular momentum. We're supplying it directly. Now this works the same way as impulse with just normal momentum. So there's a lot of parallels there to think about. Then problem 4. So to me, when I was learning this, it makes sense how something can have angular momentum if it's rotating, right? But for me, thinking about a point moving about like an axis or an angle, it just feels a lot more abstract. So let's try and tackle that with this problem. So we have some small bead. We can just treat this as a particle moving at a speed of 3 meters per second. At a particular instant, it is r from the origin, 2 meters, and its velocity will make an angle of 30 degrees with this radial line from the origin to the bead, right? So if we have this kind of particle that's moving along, it's moving along at 3 meters per second. That's its velocity vector there. And then we know some radius, right? This is 2 from the origin. And we know that the angle here is 30 degrees. Now, really quick, let's just draw some right triangle there, right? Because we know that this is 30 degrees, so this will be 60, 90, etc., right? Now that'll come in handy a little bit later. But first, let's just use the formula to determine the bead's angular momentum. So this will, we have all these quantities, so you just multiply it out. It's just 0.5 times 2 times 3 times sine 30, which is 1/2. So that you can do pretty easily. So you can get its angular momentum about this origin. But what does that really mean, right? So when you have some point like this, you can choose another point and give it an angular momentum about that point. Now, that sounds a little weird, but in this case, right, there's no net torque. And we know that because it's just moving at a constant speed, so there's no force or anything like that. And if there's no net torque, we know that angular momentum must stay constant, right? Because that's by kind of this formula, right? If it's 0, there's no change. So that means that the angular momentum must not change. And one thing interesting to note here is just mathematically how that works, right? So you might think, oh, it's moving away, so this r will get bigger. So then how does the angular momentum not change? Well, what ends up happening is, let's say the particle's all the way here. Sure, there's a really far r distance, but there's also a very small angle, right, between this velocity vector here and then that radius. And because that angle is so small, sine theta is very small. So the angular momentum turns out to stay constant. Now, obviously this is a kind of abstract topic. It's not actually physically rotating around the origin. It's moving translationally in this direction, but we can still give it some kind of angular momentum, which we're naming it here. And yeah, so even if something's moving translationally, you can still name some angular momentum about it. And this can have some useful applications. When we're doing this with a system that's rotating, that's kind of all we're doing. We're just picking a point here, and then we're just summing up all the angular momentums of these specific points using this formula. We just have a neater way to call that. It's just rotational inertia times angular velocity. Now you could try and divide that formula yourself, kind of using the relation that you learned in Unit 5. Anyways, so now let's go to 6.4. This is one of the more difficult parts of the unit. This is the conservation of angular momentum. So the overall total angular momentum of a system is the sum of its parts. And as we learned, if there's no external torque, then the angular momentum will stay constant. That's just from our impulse momentum theorem, right? So any external torque or impulse would change the angular momentum. And another important thing to note, just kind of from the key concepts from the College Board, you might get a question or two on this, is if you have a non-rigid system, let's say you have like slime on a stick, right, and you're spinning it around, right, that can alter the angular velocity but conserve the angular momentum. And the way that work is just think about rotating this kind of slime up here around with no external torque, so the angular momentum will stay the same, right? So here, as it moves faster, this will kind of go out. If you've ever rotated something that's like swishy, it'll start to disperse a bit. And then that means that we know from Unit 5, this rotational inertia will increase as more stuff is kind of farther away from the central point. The radius of these things become bigger. So that means that your I becomes bigger, but your angular velocity will become smaller in order to conserve angular momentum. Now we'll go over that a bit more in more problems. That's just something conceptual now. So here we have two disks. We have A and B, and they originally A is moving at 5 radians per second. It's rotating, and they have some rotational inertias that they're given, and eventually they stick together. And the question is asking us, find the final angular velocity when they stick together. Now this is kind of the more difficult parts of the unit. So we need to think, okay, these two disks are in a system together. Is there any external torque on these two disks? Obviously the problem tells us this, but if we just think about it logically, these two disks will exert a torque on each other, right? Disk A will kind of speed up disk B a bit. Disk B will slow down disk A a bit because B is at rest, right? But these forces, these torques will be equal and opposite by Newton's third law, right? So it's not going to have any external impact on the overall net torque, right? And what that means is that angular momentum will remain constant. So in any sort of collision like this where things stick together, angular momentum is conserved, right? And that's very important because we can apply some of our existing formulas. So now from here, the problem becomes kind of simple, right? All we need to know is that the initial angular momentum, the total, will be equal to the sum of angular momentum of B and A. However, B will have none because it's rest. So let's just think about A. So it's that times that. And then if we calculate that out, we could calculate that out, just be like 10, right? And then we know that the final angular velocity will be that times the final velocity of A plus that times the final velocity of B. And then these two are the same thing, right? So we can just kind of treat that as final angular velocity. So then in total, it's going to be the sum of these rotational inertias times an angular velocity, right? That's just some algebra. And then the important part is that these two will remain the same. So the initial angular momentum is the same as the final angular momentum. So we can effectively set these two equations equal to each other and say that IA times initial is equal to that. And then we can just plug some stuff in to find the final angular velocity. Right, so then we have 10 here, and we just add these up, so this can be 5, divide that, so then that means that the final angular velocity is 2 radians per second for both disks. So just think about that a little bit more conceptually, right? So we think about just disk A, which is spinning already at 5 radians per second, that gets slowed down, right, here, but disk B, right, which is at rest, that gets sped up. So overall, however, the total angular momentum for the entire system of these two disks remains the same throughout. So that's just something to think about. This third part you guys can do independently. You just kind of sum up the rotational kinetic energy for both before and after. You can just use the formula, the 1/2. That. Right. Okay, so now let's go to problem 6. This is kind of a classic problem. Anyone who's spinning, right? If you're a ballerina or an ice skater, if they have their arms out wide, they're going to spin generally kind of slow. If they bring in their arms, they're going to spin faster, right? So we see like Often like ice skaters will do something where like bring their arms as close as possible, right? That'll make them spin really fast. And if you think about why that happens, it's because their rotational inertia, when they do that, decreases a lot, right? And we know that angular momentum is equal to rotational inertia times angular velocity. And when an ice skater brings in their arms, their overall angular momentum won't change enough because there's no external torque on them. They're not like kicking anything, nothing's hitting them. There's no external torque besides like maybe some small friction in the ice, right? Very, very negligible. So overall, this angular momentum is effectively conserved, right? So we know that if we have a really small rotational inertia, then in order to keep it the same, angular velocity would have to be really big. And the same applies the other way. So if they bring out their arms and make their rotational inertia very big, then their angular velocity would be very small, right? So if you have like a chair or something, you can kind of spin around and see this for yourself as you bring in your arms. You'll move generally a little bit faster. So now here, this question kind of works the same way. So we have some initial angular velocity, which is like that. And then we have some final angular velocity, angular momentum, which is going to be like that. And then we know that these two quantities are equal to each other, right? For the reasons that we just described. And then here, all we can do is we can just plug in the numbers that we knew, right? So we can find this W final will be equal to these quantities over that. I changed from 2 and 1 to F and I, it's just a notation change. But here we can just plug it in. I'm not too interested in the algebra, but it's just 2.5 times this 3 over 1.5, which would be what, like 5? Yeah, so 5 radians per second. So overall, this ice skater is able to increase their speed by 2 radians per second just by bringing their arms and decreasing their rotational inertia by a bit. So we did that, and describe how kinetic energy changes, right? So let's just assume that this ice skater is at rest, translationally, so center of mass is not changing. Now, for their rotational kinetic energy, we know that that is equal to 1/2 times I times this angular velocity change squared, right? And if we just look at this conceptually, even though I times W stays the same, right? Or sorry, I times omega stays the same, you're increasing your angular velocity a little bit and decreasing your angular momentum. You're decreasing your rotational inertia a little bit, right? But the overall kinetic energy, the rotational kinetic energy, will increase because you're increasing the term that's squared. So generally, this will be more reactive in the overall equation. So we increase this a little bit. When you square it, it'll have more of an effect on the total kinetic energy. Now, you can do all the math if you don't believe me about that. But just logically thinking, if we increase the angular velocity, it'll have a larger effect than decreasing the rotational inertia if they're multiplied to be the same. So overall, kinetic energy goes up. Now for 6.5, this is about rolling without slipping. So we already know this formula. This is the total kinetic energy formula. And then if a ball is rolling without slipping, now we'll get into this more in these example problems. It has these formulas. So the center of mass, the velocity of the center of mass will be equal to the radius times the angular velocity. The acceleration of the center of mass will be equal to the radius times the angular acceleration. Now, these are kind of similar to some of the formulas you learned in Unit 5 for the relations between these two quantities. They're a little different because those were concerned with the tangential velocity of something, right? Whereas this is concerned with the velocity of the center of mass, right? Now, ideally, something's rolling with no frictional energy loss. And the reason for that is if we picture like a bike tire, right? As it's rolling along, it's not actually sliding on the ground. It's kind of just coming in contact. So any point that's actually here is technically at rest instantaneously. It's just rotating along. It's not being scraped along the pavement, which is why you, when you're riding a bike or something, you don't just feel like rubber on the ground. You just see it behind you, right? And that's because your bike will be rolling without slipping. So now let's do a little problem, right? So we have this solid cylinder of mass m. It's rolling down height h. So it rates total kinetic energy at the bottom. So I'm going to use this example to kind of talk a little bit more about rolling without slipping. So I have some cylinder here, right? And at any instant moment, this point that's in contact with the plane will be at rest, right? So effectively the rest of it, of this cylinder is rotating around this point, right? So traditionally, if you think about a cylinder that's just rotating in free space, not hitting anything, it'll have some kind of tangential velocity of these points, and that will be equal to the radius times this angular velocity, times this rotational velocity. So this tangential velocity is equal to that, right? However, here, we're essentially doubling the radius because it's rotating about this point. So the tangential velocity here is actually 2 times that because we're doubling the radius. And then at half the radius, the tangential velocity here is just that. So that's kind of where we get the formula. It's not super important you know that, but it's kind of nice to have that logical link. So essentially the center of mass is moving with a velocity of the radius times the angular velocity if something's rolling without slipping. So now to get into the problem, now this is kind of just a conservation of energy problem too, right? So right at the top here, we have some kind of gravitational potential energy. It's rolling down a height h, right? So originally, the gravitational potential energy will be mgh, just like that. And we know that that's going to be equal to the kinetic energy at the final when there's no more gravitational potential energy. It's all kinetic energy, right? So these two are equal to each other. Now, here we're linking back to 6.1, where we have, we know that the final kinetic energy will be equal to 1/2 times mv squared plus 1/2 times I times w squared, sorry, omega squared, right? Now, this is the link here. So the important part here is that we're summing this up, and that's equal to mgh. Now, what we do from here is we say that we know that the velocity per center mass, which is what we're using here in this translational kinetic energy, that's equal to the radius times this angular velocity. In other words, the angular velocity is equal to the velocity of the center mass translationally over the radius. And then now we can substitute that in here, and then substitute this in here, and then we can get kind of an algebraic expression for the rest of this problem. So I'll do that now. I'm skipping kind of the rest of these steps, and you'll see it there. Okay, so now that we're here, I've kind of just done some off-screen algebra, right? So we have our kind of total kinetic energy at the bottom here. So I just expanded that out. Sorry, it should be right here. It's 3/4 times m times velocity at the center mass squared. Now all the calculations for that is done out here. It's really just algebraic expansion of this, plugging in this rolling out splitting bit. And then from here, we know that we can just kind of find its speed at the bottom, right? Now, that means that it would just be square root of 4/3 gh, just doing some algebra there. And then next question, why does friction do no net work in pure rolling? Now, the reason for that is kind of as we described before. This point, as it's in contact with the point that's rolling without slipping, is instantaneously at rest, so it's not really moving. If we were sliding, so if we're rolling and sliding a little bit, then be doing some work, because then this point is actually moving. If you remember, like, work's equal to force times distance. So if that instantaneous friction force has 0 distance because the point is at rest, it'll be doing no work. And then here's just another question. Now, I'd like you guys to kind of do this independently. I'll show you guys the solution kind of in fast forward here. But it works kind of the same way. I just think it's good to get some extra rolling without slipping practice, as this concept is a little bit more challenging. Okay, so here I have the solution here to this problem. So just some things to note. So we have our translational and rotational kinetic energy, and then we just kind of do the same thing as the last problem. We're just plugging this formula to get its rotational kinetic energy in terms of its translational center of mass velocity, right? And then we did that. We just expand some algebra out, and then we just did a simple kind of ratio using the moment of inertia that we got here. And yeah, so just doing that, we got 2/5. And then for this part, if it starts slipping, how does friction alter the energy analysis? That just means that friction will be doing some work, which would alter the mechanical energy, be taking away some energy because it's opposing motion. And then now, this last part of Unit 6. Now, originally, when I took AP Physics, this was its own unit, gravitation. But I guess it's just a subpart, so I doubt it'll have a lot of importance in the exam this year. But all you really need to know is that if something's orbiting around another thing, let's say we have Earth kind of here, then some satellite. The satellite's mass is much, much less than the planet's mass. We see this symbol, it means it's like so much more or less by like a very high degree of magnitude. So it's like negligibly small compared to the big planet's mass. And then there's some gravitational laws, right? So the force gravitationally, this wasn't in the key concepts for this unit, but I think it's important to know between two kind of particles is kind of this formula. I guess this might have been included in Unit 2, I'm not completely sure yet. But in that case, just use this formula. This is kind of a universal constant. This is one mass, this is another mass. This is distance between the two. And it's just an attractive force. As we know, gravity is always attractive. And potential energy of gravity, now, when we're on Earth, we can just kind of use mgh. But if we're just two kind of things across from each other within the universe, that can be described by this formula. So if they're infinitely far apart, they'll have zero gravitational potential energy with each other. If they're really close, they'll have a lot because this radius is in the denominator. And anyways, so all you need to know is that there's this formula. Note that this is negative. And yeah, if you want as an exercise, you could try to derive mgh from this. Sorry, there should be like a little m, I guess, if we're keeping the notation constant, because big M would be the mass of the Earth. Anyways, and then finally, all you need to know is that if you're on a planet, the escape velocity of that planet, which is the velocity you need to kind of get away and get out of its orbit, is from this formula. Now you could calculate this out. I'm not going to show you how just for the sake of time. I'll link an article in the description for how you can calculate this. And then you need to know about circular orbits. So if something's orbiting around something else in a circle, its total energy, its gravitational potential energy, its kinetic energy, its angular momentum remain constant. This kind of makes sense. Like something orbiting something else in a circle just kind of looks like that, right? And it remains a constant distance away from the other thing. However, if we have an elliptical orbit, right, then there's some points where it's farther away from other things. Now the Earth is kind of elliptical around the Sun, so here, like we're very far here, we're very close here, right? However, the angular momentum will remain constant. That's just because of the sine theta thing and the whole radius that we mentioned before, as well as the velocity will change, right? Maybe we'll be moving like very slow here, very fast in some parts, etc. Right? So all you need to know is that the kinetic energy and the gravitational potential energy will vary. I doubt there will be that many questions about it, just kind of qualitatively knowing that kinetic energy and gravitational potential energy can change when it's in elliptical orbit, as opposed to circular. So now let's do a problem. This is the final problem of this video. So this one's a circular orbit problem, elliptical orbit problems. You don't need to know Kepler's third law or anything like that for this exam. So for this, all we're doing is we're saying that we have a satellite of mass m orbiting around Earth at radius r. Now, this kind of combines some past knowledge from other units. So what we're going to use this formula for gravitational force, because we're trying to find this kind of these quantities. They'll all be found kind of in a similar way. But anyways, so if we know that something's orbiting something else in a circle, it's going to be kind of going under the centripetal force, right? And we know that from Unit 2 that in centripetal, that kind of net force is equal to mass times acceleration. And then we know that centripetal acceleration, you know this on your formula sheet, is equal to the tangential velocity over the radius. right? So that means that this net force is equal to the mass times the velocity squared over this radius, which we got, right? And then we know the net force, since centripetal force isn't an actual force, it's a discovered force, right? So it's kind of an implied one. It's really just gravity. So centripetal force in this case is gravity. So if we plug it in, we get that Gmm over r squared is equal to m times v squared over r, right? So just canceling some things out, we can see that in this case, v squared will be equal to Gm over r, right? So if we're trying to get total mechanical energy, it'll have just kind of translational kinetic energy, because we're not concerning with how the satellite is orbiting, like twirling around within space. So we're really just looking at this 1/2 mv squared part. So in this case, we know that v squared is gm over r. So now just plugging in, we know that energy is kinetic energy plus potential energy. This kinetic energy is going to be this 1/2 mv squared, which when we plug it in, it's really just, we know that v squared is gm over r, big M, right, the mass of the Earth, and we have little m here, so that's going to be gm over 2r, because we have this 1/2 bit. And we know that potential energy, we're just going to use this formula. It's going to be negative universal gravitational constant times mm over r, right? So we plug that in, we have this. So really, it's just Gmm over 2r minus Gmm over r. We do this out, that's really equal to that. And so that means that the total energy is equal to minus Gmm over 2r. And then now, derive v in terms of Gm and r. So we kind of did that here. It's just going to be the square root of that. And then explain why k is constant in time. It's constant because the speed is constant for circular orbit. It's not speeding up or slowing down in different parts, as opposed to this elliptical orbit where it might speed up and slow down in certain parts. So that means that the kinetic energy is constant in time. Now for the full review of Unit 6. I'm going to try and keep this as concise as possible. So 6.1, we know that we have rotational kinetic energy. Something can have kinetic energy by rotation. This is on your formula sheet. And the total kinetic energy of something is its rotational plus its translational. And also, we can have rotational work. So that's just equal to the torque times the angular displacement. Similar to force times displacement, it's just kind of the analogous version of that. And work is equal to the change in kinetic energy. So here we have torque applied over an angle would be the change in rotational kinetic energy. And we also have angular momentum, right? So you can calculate angular momentum for rigid bodies or points using the formulas on your formula sheets. And then we know that angular impulse, the change in angular momentum is net torque over time, right? And that's the final angular momentum minus the initial angular momentum. And if we're trying to get the total angular momentum in a system, we can just sum up the individual parts. And if there's no external torque, just going off of the angular impulse formula, then L will stay constant, so the angular momentum stays constant. So that's kind of all for angular momentum and energy. In that bit, just know that it stays constant when there's no external torque, right? And then for rolling without slipping, we just have these two formulas, right? Acceleration one hardly really gets used. You might see that in some kind of gravitation question, if it's like rolling down because of gravity. That's kind of all you need to know there. So just know those two formulas and that you can plug stuff into those. And then for orbits, as far as orbits go, know that in circular orbits, that the energy, the gravitational potential energy, kinetic energy, and angular momentum will remain constant. That's just because it's moving at a constant speed, constant radius too. For elliptical orbits, the energy and angular momentum remain constant. That's just because there's kind of no external work being done. And however, the kinetic energy and the potential energy will vary, right? So they'll sum up to be total. They'll sum up to be the total energy, which remains the same. So the sum of these two remain the same. But as we move along the elliptical orbit, some parts might be going faster than others, might be farther apart. So those will kind of react differently. These are just the formulas you know. So we've escape velocity, just memorize that one. I don't believe it's on the formula sheet, as well as the potential energy and the total force. And yeah, so that's about all for Unit 6. I might do a problem session for Unit 6. That'll be sometime soon, and that can be used to review as well.